Hello everyone, welcome to my channel Chemistry by ANR. Today's topic is CFT, that means crystal field theory. Now this is an electrostatic model and there are certain assumptions. And what are the assumptions? The first assumption is the interaction between metal and ligand is ionic interaction, for which it is actually electrostatic interaction and is considered to be purely electrostatic interaction between the metal ion and the ligand. The ligands are considered to be point charges. And remember, this assumption later on was the limitation of CFT, because ligands are treated as point charges and not as electron clouds. Now, in case of anions or point dipoles, they are treated as point charges. And if they are neutral molecule, then what? Dipole. I mean to say is, ligands are considered to be point charges if they are anion, and point dipoles, but the dimension is of a point only if it is a neutral molecule. Now, the central metal atom generally belongs to the D series. They are of the transition metals only. So the 5 set of degenerate orbitals of D. And what is the meaning of the term degenerate? The term degenerate means of same energy. The 5 set of degenerate orbitals of D, they lose their degeneracy due to the approach of the ligand, maybe in a coordination number equal to 6 for octahedral or coordination number equal to 4 for tetrahedral. So, the 5 degenerate orbital of an isolated gaseous metal atom or ion, they generally have same energy because they are degenerate, and this degeneracy is maintained, for which they are having what? A spherically symmetrical field of the negative charge around the metal atom or ion. When the ligand is approaching in a complex, now this degeneracy of the d orbitals are lost and the average energy of the d orbitals are raised. It means if I say that the 5 set of degenerate orbitals are like this, say they are having same energy. Now they are given by small gap, but it is considered that they have same energy, and that's why I have written it within the square bracket. And these 5 set of degenerate orbitals are dxy, dyz, dzx, dx square minus y square, and dz square. Now, due to the approach of the ligand, the average energy, if this is your energy scale, the average energy of the 5 set of degenerate orbitals are raised due to the repulsive interaction between the metal clouds, electron clouds, and the ligand orbitals, metal orbital and the ligand orbital. Now, for which the d orbital split up, and this splitting of the d orbital occurs as per the pattern of the approach of the ligands. That means it depends on what type of ligand is approaching and how they are approaching. Let us see one by one. If the coordination number is equal to 6, that is for octahedral complexes, entities, coordination number is equal to 6. For them, what happens is the 6 ligand, the surrounding the metal atom or ion, there exists repulsive interaction between the ligand electron cloud or ligand orbital to the metal d electrons. So the approach is such that the orbitals like dx square minus y square dz square, which point towards the axis, they have orientation towards the axis along the direction of the ligand. They experience maximum repulsion because they are towards the direction of the ligand. The orbitals which are axis oriented, they experience more repulsion, for which they are energetically raised, and left over the three set of orbitals dxy, yz and zx, they are relatively stabilized, and so they are energetically lowered. Now this orbital setup into energetically raised two orbital dx square minus y square and dz square, they are named as EG set, higher energy EG set, and the lower energy is named as T2G set. So here we can show it in this manner, that when the coordination number is equal to 6, then the T2G set of orbitals, they are what? They are lowered in energy. So let me show you here. T2G set, they are lowered in energy. And yes, point to note over here. Please see that the lowering of the T2G set is less than the raising of the EG set. So if I say that T2G has undergone lowering, the lowering is less, and T2G means the three set of orbitals dxy, dzx and dyz. So these are the T2G set of orbitals, and what are they? dxy, dyz and dzx. Now if they are lowered 2/5 of delta O. What is delta O? The crystal field splitting energy. That is the energy difference between the EG and the T2G. Now EG is raised. The 2 set is raised. So this is EG, and the 2 set is dx square minus y square and dz square. They are raised due to greater repulsion, and we can write 3/5 of delta O, which is the crystal field stabilization energy. Delta O stands for octahedral. And this is your barycenter. That means the average energy of the d orbitals before splitting with respect to the barycenter, with respect to the average energy, the T2G is lowered and EG is raised. T2G is lowered because of comparatively less repulsion. EG is raised because of comparatively more repulsion that is being experienced for the approach of the ligands. Now, the approach of the ligand is like this. Here we can see 6 directions. The approach of the ligand for coordination number equal to 6. Now, the energy gap between EG and T2G is delta O. That is the crystal field splitting energy. And it is O is for octahedral. And I have already told you that EG is 3/5 of delta O and T2G is 2/5 of delta O. Now this depends on what type of ligand it is. That means there are some, if the ligands are changing, then their field effect is also changing. Some ligands are known as strong field ligands, and they actually produce a stronger field for which the splitting will be large. That means the gap between EG and T2G is large for strong field ligand. And for weak field ligand, the gap between the T2G and EG, that is delta O, is lowered. And How do we know which ligand are acting as strong field and which are acting as weak field? For that we have the spectrochemical series. And in the spectrochemical series, if I move from left to right, then the field effect is increasing. Field effect increases from left to right, for which we can see over here CO is a strong field ligand, Cn minus is a strong field ligand. Now at times people question then which are strong field ligand and which are weak field ligand. Now we can see that the halides are at the extreme left, so obviously they are weak field ligand. And strong field and weak field are relative term. With respect to NH3, En is a stronger field. But remember, NH3 is also a strong field and En is also a strong field. So it is actually taken H2O as standard, and the ligands which are on the right side of H2O are actually very strong field ligand. To the left, the field effect gradually decreases. So that is how you need to see it. Now, for an octahedral complex, if I say it is octahedral, then what is the energy gap? Energy gap is T2G and EG. Suppose I say D1 configuration, then if I say D1 configuration, what will be the electronic configuration of T2G and what will be the electronic configuration of EG? It will be obviously T2G1. D2, because T2G is actually having what? It is actually having 3 set of degenerate orbital. So D1 का मतलब है कि it is T2G1. D2 का मतलब है T2G2. D3 का मतलब है T2G3. Like this. So for this I can say what? I can say here D1 is T2G1 EG0. Now D2 is T2G2 and D3 is T2G3. Now after this, we need to see whether it is a weak field ligand or a strong field ligand from D4 and onwards. If I say D4, I'm going back to that diagram. If I say D4, if it is a weak field ligand, then what happens? If it is a weak field ligand, that means the gap between T2G and EG is less, and the fourth electron for a weak field ligand goes to EG. And then in that case, we are going to write T2G3 and EG1 for a weak field ligand. Why? Because for a weak field ligand, the gap that is delta O is less than the pairing energy, the energy that is released. Now here we can see what is happening. That is, for a weak field ligand, here for a weak field ligand, pairing energy is higher than delta O. And we can see configuration as T2G3 EG1. And it forms high spin complex. So let us compile the concept over here. So I said pairing energy will be high. Now over here, a type of complex, whether it is a high spin or low spin complex, that what it will be. So it will be since we are getting unpaired electron, so this is a high spin complex. This is a high spin complex. Now, why high spin complex? Because there is no unpaired electron. There is no paired electron. The electrons are unpaired. Now, for a strong field ligand, pairing occurs. Why pairing occurs? Pairing energy is lowered than delta O. So, pairing will occur for a strong field ligand. It is strong and it can pair up. So, the fourth electron will obviously come to T2G only, and it will be T2G4 and EG0. And since pairing has taken place, okay, so since pairing has taken place, it is a low spin complex. Okay, so this one, T2G4 EG0, and this effect is known as strong field ligand, and they are low spin complexes. So strong field ligand, they are forming low spin complex. So D4 is over. Now if I talk about D5, what it will be? If it is a weak field ligand, weak field means what? Pairing energy. Pairing is not possible for weak field. Remember, in this manner. So if pairing is not possible, T2G can hold single electron up to 3. Leftover 2 electron goes to Eg, and it is T2G3 Eg2. And since they are all unpaired electron, it is high spin complex. And over here it will be T2G5 Eg0. T2G has 3 set of degenerate orbital, so it can maximum hold 6 electron, and this is a low spin complex again. So you go to D6. If it is D6, then it will be what? It will be, this time we need to understand what happens for a weak field ligand if it is D6. This is 1, 2, 3. Now 4, 5, and now here 6, because the filling of electron in these orbitals follow all the rules as you have seen in case of filling of electrons in other orbitals. It follows Pauli's exclusion principle, Aufbau rule, everything it follows. From a lower energy to higher energy it will be filled up. So T2G3 first filled up, now Eg is filled up, and then pairing occurs. So here we can see T2G4 and Eg2. So this is it. It is D6 configuration. What will happen? T2G4 Eg2. So here, do we have it anywhere? We are not having it right now. So let's see. It is like this. Now if it is a strong field ligand के लिए क्या होगा? The pairing will occur and Eg will actually not get any electron until and unless T2G is completely filled up, and T2G can hold a maximum of 6 electron. So it will be T2G6 and Eg0 for D6. D7. Now D7 means what? T2G and Eg. At first T2G3 Eg2. Okay, so that makes it 5. Leftover 2 will occupy T2G only. So it will be T2G5 Eg2 for a weak field ligand. Strong field में pairing होगा भी तो it can hold a maximum of 6, and the 7th electron goes to Eg. So this is a D7 configuration. So likewise you have to fill up the electrons. Now moving on to crystal field splitting in tetrahedral coordination entity where coordination number is equal to 4. Now it gets reversed. This time T2, not G. G is the symmetry element. So for tetrahedral we write T2 and E. T2 is raised and E is lowered in energy. T2 is raised because for a coordination number of 4, now the metal, the central metal atom, it has approach of ligand in such a manner that the ligands which are in between the planes, they are raised in energy due to maximum repulsion. And the lowering of the energy of the E orbital, that means dx square minus y square and dz square, is greater than the raising of the T2. So now this splitting is delta T for tetrahedral, which is 4/9 part of delta O, for which we can say that the orbital splitting energy are not sufficiently large for forcing pairing of electrons. So they are not sufficiently large. Therefore, low spin complexes are rarely observed. So the pairing doesn't take place here, and low it is not sufficiently large, the orbital splitting, and for which low spin tetrahedral complexes are rarely observed. In order to form low spin tetrahedral complexes, there should be spin pairing, electron pairing, and for that you need pairing energy to be lower. Okay, so now G stands for symmetry element, which is actually known as Geradé. It is not here, so you need not worry for as of now for class 12. Now, color in coordination compounds. Color in coordination compounds depends on presence of unpaired electron. It depends on type of ligand. Now, transition metal complexes, they are generally colored. Why? Due to the presence of unpaired electron. That is what you will actually see. That means that some of the visible spectrum is being removed from white light as it passes through the sample, and so the light that emerges is no longer white, and what you see is the complementary color to what is absorbed. So here we can see the color of light that is absorbed and the color of the coordination entity. That means it is just the complementary yellow, complementary coming up to be violet. So this is the complementary colors, and so you need to see this table for that reason. Now I said color of the coordination entity depends, or coordination complex depends on the type of ligands. Now like TiH2O whole 6 3 plus, hexa aqua titanium ion, and that is titanium 3. It is a violet colored complex. Now, what is the electronic configuration? Here, titanium 3 plus, I said, it has 3D1 system, and this D1 electron, this is a coordination number equal to 6, and this D1 electron is actually in T2G1. Now, with extra energy being supplied, this electron gets transmitted to the EG. And this transition, electron transition, actually results in the color of the complex, because when this electron returns to the ground state, it emits the complementary color that it has absorbed. So, the crystal field theory attributes the color of coordination compound to DD transition of the electron. So any question which is related to the color of coordination compound demands electronic configuration to be written. And once you write the electronic configuration, you need to see whether there is any unpaired electron in it. If there is any unpaired electron, it automatically, obviously undergoes transition, which is DD transition. And why the name DD transition? Because the transition is between the d orbitals that has got already split up due to the ligand approach. Now, it is important to note that in absence of ligand, crystal field splitting does not occur. And if ligand is absent, then the substance is colorless. Like removal of H2O from this complex will render what? It to be colorless. Now, you have seen this experiment in your lower classes, that is hydrated copper sulfate, blue vitriol. When you heat it, it gradually loses its color and finally becomes white in color. Why? Because the entire water molecule is not lost all at once. First it loses one, and then when it loses in stepwise manner. So, finally, when all the H2O molecule as ligand it is lost, the color is white. Now, the influence of the ligand on the color of the complex is seen in nickel, in hexa aqua nickel 2 ion, which forms when nickel 2 chloride is dissolved in water. Now, if the didentate ligand is attached, like EN, ethane 1, 2 diamine, then what will happen? So one by one, if you keep on attaching, introducing En to the structure, so what is happening? You can see this green color goes to pale blue, and this was En is a didentate ligand, and so here it was coordination number equal to 6. To remain 6, it is 4 plus 2 into this is 1. Why? Because En is 1 and its denticity is 2. So coordination number remains 6 only. Color changes due to the change in the ligand. And now you can see this was the previous, that pale blue solution. This pale blue solution again gradually changes its color by introduction of another En to it. So when another En gets introduced, didentate, so this reduces to 2 and then En whole twice. The color goes from pale blue to a purple color or a blue, a deep shade. Now here again, this thing again introduces another En to its structure and it becomes violet in color. So what I mean to say is, if the ligands are changing, the interaction changes, the color of the complex also changes, because the ligand field, the ligand effect is important in to actually judge the electronic configuration of the central metal atom or ion. Likewise, if it is a strong field ligand, it will automatically pair up the electrons and it will actually not render any unpaired electron. So likewise, and if it renders also, wherever the unpaired electron is more in number, intensity of the color will also be greater. So color of coordination compounds depend on type of ligand. It depends on electronic configuration of the central metal atom or ion, presence of unpaired electron that can cause DD transition. Now, we know gems in astrology, like ruby. The color of ruby is very, very vibrant. And ruby is actually aluminium oxide. It contains small percent of chromium ion which has a D3 configuration, Cr3+. Now, why this random color? Why this beautiful color? Because its structure contains unpaired electron and it undergoes DD transition. That gives this beautiful color, emerald. It also contains Cr3+ ions in octahedral manner, and it actually gives this vibrant color. Here again DD transition takes place. So these are the limitations of crystal field theory, which I, in the very beginning, I told you, considering it to be point charges. That is what I said. Other than that, let us see. Now, it has its success in explaining the structure, explaining the color, explaining the magnetic properties. Of course, presence of all paired electron diamagnetic, unpaired electron paramagnetic, and if the paramagnetism is greater, means number of unpaired electron is greater, we can also judge what is the bond moment by the formula mu b is equal to root over of n into n plus 2 Bohr magneton. That is a bond moment. That also we will get. Now, limitation kya hai? From the assumption that ligands are point charges, what it does? It follows that anionic ligand should exert greatest splitting effect. But what did we see in the spectrochemical series? The chlorides, they are on the lower side. Anionic ligands, the chlorides, the bromides, they are at the low end of the spectrochemical series because they are actually weak field ligand. So it does not take into account the covalent character of bonding, type of bonding between the ligand and the central atom. So these are the limitations of CFT, which later on was resolved by LFT and MOT. And that is not right now in your syllabus. Now these are the very important in-text question. Based on the basis of VBT, you have to explain that nickel ka ye cyanido wala complex is a square planar. Obviously, then you have to derive and show that it is dsp2 hybridized and is diamagnetic. That means having all paired electron, that you have to show by the electronic configuration. And this is a tetrahedral geometry. That means you have to show, derive and show it is sp3 hybridized, derive and show that it contains unpaired electron and hence paramagnetic. Now, the next question, NiCl4 2 minus is paramagnetic, the other one is diamagnetic. You have to talk about the field effects, like this CO is a strong field ligand and Cl minus is a weak field ligand. Obviously, strong field ligand will cause pairing of electrons, and that you have to show. Like nickel over here is Ni0 oxidation state. So how it is occurring? Pairing is occurring. Now if it is Ni0, it is what? It is 3d8, and then what happens over there is 4s2, and so the outer electrons are getting involved. Tetrahedral sp3, it is getting involved. So here this is quite important, how to derive, okay, that this is diamagnetic while both are tetrahedral. Why this is diamagnetic? Because all are paired up electrons, and Cl minus is a weak field ligand, for which वहां पे क्या होगा? There will not be any pairing of electrons, से paramagnetic रहेगा. H2O, H2O आयरन के साथ देखो स्ट्रांगली पैरामैग्नेटिक है, बट आयरन के साथ वही Cn माइनस इज वीकली पैरामैग्नेटिक, क्योंकि as per the spectrochemical series H2O is in the lower side than Cn minus. So this is a stronger field ligand. So this is a stronger field ligand for which it is weakly paramagnetic. So you need to write the oxidation state, you need to write the electronic configuration, and since it is weakly, that means the number of unpaired electron should be coming less in this compound than the other. Now CONH3 whole 6 3 plus is inner orbital complex. क्या करना होगा? You need to first write the oxidation state. Plus 3, need to write the electronic configuration. In approach of the ligand NH3, which is a strong field ligand, there will be pairing of electron and there will be involvement. See, coordination number is equal to 6. So obviously it is D2sp3 configuration. I mean here that's why what is happening is D2sp2 configuration. No, this, so it is what is happening is inner orbital. Why? Because when you are using D2sp3, then your N-1D is involved, NS and NP is involved. It is involvement of this N-1D2, NS and NP3, and so it is an inner orbital complex. And in case of nickel, it is outer orbital complex. Why is it so? Outer orbital complex, because over here it will be sp3d2 configuration. And so NH3, in one case we can see it is pairing up. Where it is pairing up, NH3 is acting as a strong field in over here with cobalt, and it pairs up electron for which the inner d orbital are vacant, they are available. And in the other case, this NH3 is weak field when it is with nickel. So for same metal atom, same ligand atom or group of atom, for same ligand, the type of metal also is a factor. With one type of ligand, it is acting as a strong field, and with another type of metal ion, it is acting as a weak field. So with some metal ion, it is acting as strong field, like in cobalt 3 plus it was quite a strong field, but in case of nickel it was a weak field, a comparatively less strong. Predict the number of unpaired electrons in the square planar geometry. Again, the same thing. You have to find out the oxidation state of platinum. Accordingly, you have to write the electronic configuration. Cn minus is a strong field ligand. So what you have to do over here, Cn minus is a strong field ligand. So it will actually pair up the electrons. After pairing up the electrons, how many unpaired electrons are remaining? That is it. Next, aquo is written, it will be aqua. Manganese 2 ion contains 5 unpaired electron. So you need to show this, while the other cyanido ion contains only 1 unpaired electron. With CFT you have to explain this. So obviously first you need to draw the structure. It is what? First write the metal. So you write it manganese first. Aqua means H2O whole 6. Now no other ligand is present, you close it. Manganese 2 means this is a 2 plus. So obviously you have to write the electronic configuration of central manganese 2 plus. And what about the other hexacyanido? That means MnCN whole 6, and then over here cyanido ion. So it is what? This will be, again, you have to find out what is the electronic configuration of this central metal ion. Okay, so this, after doing this, you go to the bonding of metal carbonyl. Metal carbonyl bonds, they are the metal atoms are the transition metal atoms. So let us see, like tetracarbonyl nickel 0. It is what? Tetracarbonyl nickel 0 means NiCO whole 4. This is tetrahedral. Obviously that means it has sp3 hybridization. Whereas pentacarbonyl iron 0, that means pentacarbonyl iron 0 means FeCO whole 5. This is trigonal bipyramidal. That means this should be a TBP structure. Means what? It should be sp3d. While the other hexacarbonyl chromium, so hexacarbonyl chromium means Cr and then CO whole 6. This is octahedral. That means it can be either D2sp3 or sp3d2. Now, since this is a strong field ligand, so it ought to be D2sp3. So like this, we know what should be the structure, but keep in mind that for these, the carbonyls, you need to see the oxidation state, you need to see the coordination number and decide what will be the structure. Now this is something which is very important, that is synergic bond. What is that? Both way of bonding is known as synergic bond. Now when metal carbon bond in metal carbonyl is actually seen, it possesses, the metal carbon bond actually possess both sigma and pi character. Now we can see this is the sigma bond, that is sigma overlap, head-on overlap that is taking place between, by the donation of the lone pairs of the electrons on the carbonyl carbon to the vacant orbital of the metal. Now the metal to carbon pi bond, metal to carbon, the pi bond that you are seeing, this is formed by the donation of pair of electron from filled d orbital of metal into the vacant antibonding of pi star orbital of the carbon monoxide. So that's why it is a synergic bond, because the forward way of bonding is the the lone pairs of the metal carbonyl being donated to the vacant orbital of the metal, and in return what is happening over here, the metal actually donates the pair of electron from its filled d orbital to the vacant antibonding pi star of carbon monoxide. Now, the metal to ligand bonding, it creates a synergic effect, two-way effect that strengthens the bond between CO and metal, as if it is a two-way bonding. That is, this is considered to be a forward bond of sigma, and the backward bond, and that is known as, or the synergic bond, is your pi bond. Now, importance and application of coordination compounds. There are various importance, various applications. You just need to go through, like reagents, EDTA, DMG. They are used in a laboratory for actually estimations. Okay. Now, hardness of water is also estimated using EDTA. So these are also used. Chlorophyll contains what metal ion, hemoglobin contains what metal ion. These all things are important questions. Okay. Now, gold, it actually combines with cyanide in presence of oxygen and water to form this in aqueous solution. Now, gold can be separated in metallic form from the solution by the addition of zinc. You can actually get the gold. So these techniques are nowadays used widely. Now, purification of metal, that is also very, very important thing that is being done. The impure nickel can be converted to the nickel tetracarbonyl, which is decomposed to yield pure nickel. And then I said hemoglobin, what metal is present. Then I said like vitamin B12 or cyanocobalamin. Okay, so this the anti-pernicious anemia factor. Okay, so this is a coordination compound of cobalt. So anyone can ask you which metal is present over here. Coordination compound is used as a catalyst also in many industrial processes. This is Wilkinson's catalyst is this. You need to remember what is Wilkinson's catalyst and for what it is used. It is used for hydrogenation of alkenes. Now, here again, you have to just give it a reading in order to understand where, in which field, which coordination compound is being used. Like cisplatin can be used many times in the chemotherapy and medicinal purposes. So how you are using the coordination compound is of importance. So the chapter of coordination compound theory part is over. Go through the videos, see them stepwise, and study properly till we meet in the next unit. Till then, bye all of you.